Welcome to our next session at the Cyber Tech and Risk Trust Cloud Virtual Conference. Very pleased to have our friend Kieran Miller to join the session. Kieran is a chief architect at Garantir, a cybersecurity company based in San Diego, California. And with over a decade of cybersecurity experience, Kieran has expertise in multiple dimensions of enterprise security, from data security, identity access management, to secure software development and network security. And Kieran will talk about securing the CI/CD pipeline in a virtual DevOps environment. All right, so I will pass the control to Kieran. Kieran, all yours.
Thank you, Brian. Appreciate the introduction. It is definitely beautiful here in San Diego. And we are excited to be here to talk about this important topic. So as Brian said, we are Garantir. We are specialized in this space. We've been dealing with this for quite some time. And we're excited to come here and talk about how to secure the CI/CD pipeline. And in order to talk about that, we need to talk about how does one attack the CI/CD pipeline. Now, today, this is commonly being referred to as a supply chain attack. So what is a supply chain attack? That's essentially where an attacker wants to attack high-value organizations with the goal of really getting them by attacking third-party software. So that third-party software is used as the attack vector to get into those, to their high-value targets. There's obviously been some recent ones all over the news, SolarWinds, that happened, and there's some other ones in the past. And we're starting to see them with slightly more increased frequency. So who needs to secure the supply chain? The obvious answer are the tech companies, but really it's any company that produces software, which nowadays is almost any company. Now, some companies produce software as the core bread and butter of what they do, whereas other ones may produce it for internal stakeholders for things like managing the servers or automating certain processes. No matter who it is, you still want to secure that process. And today we're going to talk about some guidelines on how to do that and how to really do it in a meaningful manner. So there are some great frameworks that are already out there. Google has a SALSA framework, Microsoft has SCIM, the CNCF has some best practices to follow. They all have really great recommendations in there, and that's what we're basing our talk today on. This is not in lieu of reading those. You definitely should go read those frameworks. They do a good job of outlining what to do and threat models and that kind of thing. But we're going to really focus on a few of their best practices. We're limited in time today, so we're going to focus on a couple things that are common amongst these frameworks. One is verified reproducible builds. We'll go over in more detail what that means in a little bit. How to protect your source code repository. At the end of the day, the source code repository is the source of truth, and so we want to protect it. Using cryptographic attestations to attest to the fact that a certain build meets certain criteria. And then, of course, if you're using cryptographic attestations, those are only meaningful if you protect the keys that are used to produce those attestations. So in order to talk about all this, we need to talk about how software is typically produced. And that's usually done in a CI/CD pipeline. And in a high level, that looks roughly like this. You have a developer who commits code to the source code repository, and that's going to trigger a build. And what that is the build server is going to go off, get that source code and compile it, build it into its final binary format. It's typically going to then sign it, and then it's going to run a battery of tests. And then at that point, the build is complete. Now, some people are doing full CI/CD, which the CD meaning it actually delivers the final result, where some are mainly just doing CI, continuous integration, but the final result is only released on maybe a quarterly basis. There's also some other things that'll differ. Maybe you're doing other types of things like fuzzing and security scanning and all that. But the bottom line is this is the general flow of how the software is built. So with this in mind, how does an attacker attack this system? So keep in mind that in order for the supply chain attack to be pulled off, the attacker has to be able to masquerade their malware as the legitimate software that's produced by the company. And so in order to do that, they need to sign their malware with your key. Now, there's a few ways that they can pull this off. The first is to steal the key itself. This is arguably the worst case scenario. In this case, they can do what's called offline signing, and they can just sign as much malware as they want until you revoke the certificate. So this is a pretty bad situation. The second situation, if they can't steal the key, is they can compromise the build server. If you compromise the build server, then as long as you have an online access to the build server, you can sign code at will, even though you haven't stolen the key. This is what happened in the recent or semi-recent SolarWinds attack. The next attack vector is the source code repository. So in this case, you're actually injecting the malware into the source code repository. Now, this is not ideal for the attacker because it does leave a permanent record of the malware. And so if you're following decent practices like code reviews, the developers are going to see that. So it's not ideal, but it's certainly possible. And then the fourth attack vector is the developer workstation. So in this case, it could be the workstation itself that was compromised, or it could be that the developer itself is the insider threat. So in that case, the workstation or the developer is used to then push the change to the repository, which then cascades down. So how do we prevent against this, right? So at a high level, we want to ensure that the code in the source code repository is what I'm going to just loosely say is good, free of malware, what we intend it to be. And then the second thing we need to do is we need to ensure that the code that we sign exactly matches what comes from the source code repository. Now, that second part is a little tricky because you end up signing typically the binaries, whereas the code that's in the repository is the source code. And so you need to find, and this is where the verified reproducible builds are going to come into play. So with all that said, that sounds great in theory that we want to do this. How can we actually get there? So again, still staying at a high level, to protect the source code repository, we want to first protect access to it, right? So we're going to skip things like basic security practices that you should be following, like principle of least privilege and all that. But we do want to enforce stricter security controls like multi-factor authentication, device authentication, that kind of stuff to the repository. And then we want to be able to scan the code in the repository. And so we'll get into how to do that in a moment. And then we also want to deploy a secure code signing environment. So we want to protect the keys from theft. That's where we're going to use a hardware security module for that. We want to restrict users to proxied access to using those keys in the HSM. And then we want to do the biggest challenge, which is we want to use those verified reproducible builds to ensure that we're only signing code that comes from the repository. So now, let's just say hypothetically you could build that out. You're going to still run into some challenges. So for example, in protecting the source code repository, what if your source code repository doesn't even support multi-factor authentication? But it's very popular now to be in the cloud using a third-party hosted source code repository. And if they don't support device authentication or multi-factor authentication, how can you still go off and enforce those controls? Performance, as you start doing these verified reproducible builds, we're going to see what's the effect on performance and can you bypass that? The hash validation, of course, so this is the verified reproducible builds. How can we even do this in a meaningful manner? And then integrations, right? So typical big companies, they're producing software for Windows, for Linux, for Mac. Is this going to work? Is this kind of framework going to work across the board, or are you limited to only certain, only a subset of the projects that you build? So starting from the basics, going back to those attacks, we're going to come back and show how to deal with each one of those attacks. So the first one, just don't leave your keys under the doormat is a common expression in this space. So the key that's used to sign the code, you want to protect it. And what that means is instead of having that code signing key sitting, on the build server itself or, in software, you want to get that in hardware level protection. Now, back in the day, this was, getting a hardware security module or some type of protection for that was cost prohibitive for some smaller companies. But in this day and age, there's really no reason not to use it. The cloud vendors offer HSMs at very more than fair prices. They offer key management solutions, KMS options, where you're effectively paying $1 per key per month. The HSM vendors have HSM as a service. And then of course you can still buy your HSMs on premise. There's really no reason not to be using it, even if you're a small company. So get the keys in the HSM, and that way, you know, at least they're not being stolen and people aren't doing offline signing attacks. Once you get the key in the HSM, you're going to run into potentially a problem. And because back before the key was in the HSM, you could bring the key to the software to do the signing. Now you can't. You have to bring the software to the key. And the sort of slow or naive approach to doing that is to upload the code to sign to a server that has access to the HSM, perform the signing, and then download the results. The problem, there's two problems with that approach. The first and the main one is that it's very slow. As the file sizes increase, the network bandwidth to upload and download, it starts to, it shows its head, and you start to get very bad performance. And so that's obviously not desirable in a CI/CD pipeline. And then the second issue is that uploading executable code to a server that has access to the HSM is just generally not a good idea from a security perspective. So a better approach is to use something called client-side hashing. And that is, since a digital signature is made up of two components, the cryptographic hash and then the private key operation, and the hash does not require the private key, you can do the hash on the client side before sending the data over the network. And the result is, because the hash function always produces a fixed length that's small, it doesn't matter if you're signing a 2 GB file, the data sent over the network is going to be very small. And so you can still sign in extremely fast times. So now that we have the keys in the HSM, we know we're not degrading performance to do that. How can we go off and do this verified reproducible build? So how can we protect against the attack on the build server itself? And so what does it mean to be verified reproducible? At a high level, what we're doing is we're taking advantage of reproducible compiling or reproducible building, sometimes referred to as deterministic builds. And that is, from the same set of source code, if I then build that or compile it, I will always get the same exact outcome. So byte for byte, the hashes will line up. It'll be the exact same match. And you can use that fact to then build a system on the signing to independently verify that what's being signed matches what comes from the source code repository. So we call that automated hash validation. It's just another way of talking about verified reproducible builds. It's the same concept. So here we have the source code repository and the build server, the build is triggered. And now the build goes in, it does the compilation activity. And now it sends the hash over to the signing server, because we're doing client-side hashing. And now the signing server says, hey, is this a hash that I want to sign? So it reaches out to the source code repository, performs a deterministic build, computes the hash itself, and then says, do these hashes match? And if they do, then it can offload that to the hardware security module or key management service or whatever you're using to then sign. So it's acting as an independent verifier and acting as a gateway before it allows any signatures to occur. So let's take a look at what this actually looks like in action. So here we have a system where we're actually have a signing server sitting in front of an HSM, and we're going to enforce some policy to turn on this automated hash validation or verified reproducible builds. So here we're changing the policy on the key to enforce the validation. You'll see that happen right there. We save that. And now when we try to sign something that does not come from the source code repository, we see we got a failure there. This failure was not because of the actual hash validation, but more because of the signing server didn't know where to pull the source code from and how to do the verification. So it just said, hey, you didn't give me all the information I need. So now in this configuration script, we're telling the signing server, hey, it's this project, it's this revision number. And now we run the attempted attack at signing something, and we get a failure again. This time the failure is because of the hash validation. And you'll see that the system says, hey, the hash that you gave me to sign does not match the hash that comes from the repository. And so it didn't work. But on the flip side, you'll see here, this is Team City, but it's just showing a build server. Doesn't matter that it's Team City. This could be Jenkins or anything else. In this case, the signing works just fine. You see all the successes there. And that's because the build server is signing code that comes from the source code repository. So all the hash validation passes. Now, a natural question with this is, well, we went through all that work to get the client-side hashing to get performance better. What's the effect of the verified reproducible builds on the performance of the CI/CD pipeline? And you probably noticed that when we ran the signing command, it took a little while in order for the validation to occur. And so for this reason, there's actually two modes that you can do the validation. There's pre-sign and there's post-sign. And these modes are exactly what they sound like. In pre-sign mode, the validation occurs before the signature is generated. And in post-sign mode, the validation occurs after the signature is generated. And so pre-sign is a preventative control that has a lot of security. And so it's great for production releases, things that you do less frequently. Whereas post-sign is a detective control and it has high performance and it's really good for higher use cases like in your CI environment. So pre-sign is effectively more focused on security, whereas post-sign allows you to balance security and performance pretty well. And so let's take a look at what post-sign validation looks like. So here we are, we're modifying the keys policy to do post-sign validation. And so now we're going to run that same exact attack script as before. Now this time you'll see it immediately signs. So because we're running in post-sign mode, the signature immediately occurs. And now we get the message saying, hey, that hash was a mismatch. And by the way, we already signed this. So that's letting you know, maybe you should go revoke the cert and you should start some triaging because we signed something that doesn't match what comes from the source code repository. So while it's not great that something got signed that shouldn't be signed, you are trading that out for performance and still getting enough heads up so that you can do something immediately, like revoke the certificate before something really bad happens, like the malware is distributed out to end users. You can even take this concept a step further to enhance performance. And so this is a rough framework of what happens in a CI/CD pipeline. Basically, the idea is everything happens serially. But because when you do the verified reproducible builds, you end up with a duplicate copy of the binaries, you can actually take advantage of that to offload things in parallel. And so what that looks like is this. So now we're able to take some of the tasks that were done serially before and do it on the second copy of the binaries once we verify that the hashes match. And the end result is that the total time taken to produce, to do the build goes down. So I should emphasize that's the total wall clock time, not the total CPU time. So the total time a developer waits after committing to the repository, that goes down. But it's done at the expense of an additional machine that's used to do the verified reproducible build that's then offloading some other tasks. So let's see what that looks like in action. Here we have, we're intentionally injecting some malware into the code. This is a SQL injection that we're injecting. We're gonna go ahead and commit that to the repository, and we're gonna trigger a build based on that. And what this is gonna show at first is doing that by default. That just allows everything to operate normally because the hashes will match. Because what happened is we actually injected the bad code into the repository. So now what we're going to do is we're going to say, I not only want to do the hash validation, but I want to run some static analysis too. And so because we have that duplicate copy of the binaries, we're able to run the static analysis, and that's where you'll see it fails. So the hash validation tool was actually able to run the analysis and say, yes, this matches what comes from the repo, but we have a code scanning failure. Now, that previous one we did in pre-sign validation mode. Now we're going to switch it to doing it in post-sign validation mode. So in this case, the build should complete successfully, but we should get a notification later on that, hey, there was a problem. And the build should complete faster this time because we're doing the pre-sign mode. And there we see that the build completes successfully, and the time it took to do the build was faster, but we should still get a notification saying, hey, there was a problem, and there it is. We see a validation failure for that build. So it allows you to put these security controls in place and balance where you want to have higher performance. So that's just kind of saying, so there's two things we played with there. One is pre-sign and versus post-sign mode. And the other is taking advantage of the fact that there's now duplicate copies of the binaries, so you can offload things and run tasks in parallel. So now that we have our keys in the HSM, we're doing verified reproducible builds, so we know that we're only signing code that comes from the source code repository. The next thing is, how do we protect the source code repository? If we're going to treat it as a source of truth, we better protect it. And so there's a few things that you need to do. So you want to protect it with security controls, MFA, device auth, that kind of thing. You want to use cryptographically sign your code commits. Scanning for malware and bugs, we just showed that in the previous video, how that works. And then you want to do code reviews as well. We're not going to talk about code reviews today, not because it's not important, it's actually really important. And it's especially really important if you want to avoid insider threats and things like that. But for the sake of talking about some technical stuff, we're going to show how you can use the same paradigm that we've been using for the code signing to actually enforce these security controls on repositories, even if the repository doesn't support it. So this idea works even if we're not talking about source code repositories. It works for SSH to servers, RDP. The end idea is that when you're talking to these servers and you want to turn on MFA or these additional security controls, traditionally that's done at the application layer, right? So if on a Linux server, you install a PAM module, web applications, you add some code, and you start adding that into the application itself. But if your application or your server doesn't support it, then you're kind of in a bad position, you're stuck. However, if you move the controls down to the transport or the session layer, you can actually enforce these controls without affecting the downstream resource. So even if the source code repository doesn't support it, you can enforce it. And the way you do it is by using key-based authentication, which almost every source code repository supports. And by proxying the keys in an HSM or some key manager, just like we're doing for code signing, you can enforce the security control when you attempt to use the key, and that'll have the downstream effect of enforcing those controls when you try to access the repository, even though the repository doesn't support MFA or device authentication. So here's an example using GitHub. GitHub changed its capabilities recently, but this was all recorded before you could do any MFA or anything like that. So no capabilities there. We're just we're going to use this test project to show how we can transparently enable multi-factor authentication onto the repository, even though the repository didn't support it. So here we are with the test Git project. We're going to go ahead and modify the README file. And so first we're going to commit the change. That of course is a local commit. So that goes through just fine. Now we want to push the change to the repository. When we do that, we're using a key that's proxied, and we've turned on the capability to turn on MFA. So here we are putting in our MFA. In this case, we're using OTP codes for MFA. And only once we complete that, the MFA, will the push actually complete, because only then are we allowed to use the key. And so as a result, now the code is pushed to the repository. And when we come back to over here, we should see the new change. And there it is. So we were able to transparently enforce the security controls onto the repository, even though the repository didn't support it itself. So that's a pretty powerful capability. And you can layer whatever controls you want in. Multi-factor authentication, device authentication, where you say, yep, that's Kieran Miller, but he seems to be using a computer that we don't trust. Sorry, you can't commit code from that machine. You can do all kinds of stuff like that. So with that, you can put everything together. And this is a little bit of an eye chart here. But this is showing the CI/CD pipeline with everything baked into it, but still working. So the developer is committing code to the repository. When they do that, multi-factor authentication and device authentication is triggered. All the commits are code reviewed. The build server, when it's trying to sign code, it has to reach out to the signing server with the keys in the HSM. That's going to trigger a verified reproducible build so that we're only signing code that came from the source code repository. And then, of course, from there on, once you have the final result, you run your testing and you can do full CD if you'd like to, or you can store it somewhere. But the whole process works within what we're used to seeing in the CI/CD pipeline and does it without breaking backwards compatibility with existing processes. Now, of course, we've been doing demonstrations here. We're using our own product, GaraSign, to do that. It's built to do all of this and more. So it handles the verified reproducible builds, the increased security controls on source control repository access, all the code scanning. It can talk to third-party tools for that. And it supports it across a host of client integrations, right? So it's not like this only works on Windows. The same idea will work on Mac, Java, Linux, you name it. The idea works. And we make that possible by providing all the cryptographic API integrations that you need to make it work with the tools that you use today. So you don't have to change. If you're signing with SignTool, you'll continue to run with SignTool and get all these other benefits in place. Same thing for CodeSign, Jar Signer, et cetera. And GaraSign supports a host of other use cases as well. So underneath the hood, when you're doing the source code repository access, that was actually using SSH underneath the hood. So that's actually a demonstration of both the code signing capabilities as well as SSH. But there's a lot of use cases that use keys under the hood. And so really any use case where you have keys, cryptographic keys that you want to proxy and protect, and you want to apply policy on and audit, that's what the platform is for, and to seamlessly work with the same tools and products that you use today. So Brian, I appreciate being here. It was great to do this chat. Let me check what we have here in the questions. I see, what role does staging play in securing the SDLC? So in our world, we believe that the keys to protect the environment should be protected regardless of whether it's production, non-prod, et cetera. You want to catch these things early on. So everything that we talked about today can be applied to all the environments. And then those parameters that we gave, the pre-sign validation versus the post-sign validation, that is what you want to tweak with to say, hey, in my non-prod environment, or when I'm signing with my non-prod key, I do that a lot. Maybe you do that 1 million times a year based on your builds, but your production release, you're only doing that quarterly. So then you want to use the pre-sign validation in production and the post-sign validation in non-production. And that really gives you that good, healthy balance between performance and security. And I see another question on verified reproducible builds. And so that actually, the ability to do the reproducible build, most compilers have those capabilities nowadays. There's a whole movement to move towards reproducible builds. In general, even if you're not doing it for the signing aspect, you want to move towards reproducible builds because you want to know that, you're producing software that's based on the source code that you'd expect. And so there's some great resources out there about doing reproducible builds. And like I said, a lot of compilers and builders have a switch in them nowadays to just say, hey, I want this to be reproducible. How to educate developers about DevSecOps, man, that's a loaded question. There's a lot there. To be honest, it's such a we move quickly in this space, so you really got to stay on top of things and play around with tools. But at the end of the day, the fundamentals haven't changed, right? We're in the cloud, we're on premise. There's some things that change, but our fundamentals are still the same. We're still producing software. We're putting it into a source of truth. We're building that software, and then we're signing in that software, and then we're delivering the result. And so your basics still need to be done in a solid manner. You need to protect those keys. You need to verify that what you're signing actually comes from the source code repo, and you need to protect that source code repository. Whether that's in the cloud, on-premise, hybrid, it should work no matter what. Those core fundamental philosophies should always hold true. Well, thank you, Brian. It was a pleasure to be here. Love talking about this stuff, and looking forward to the next time.